All right, our two learning goals for 5.2 are I can determine whether or not events are independent or dependent and find the probability of these events. And the second one is I can find conditional probability. So what we're going to be talking about is compound events, like when you have more than one thing happens, and how do you find those? And those depend on, again, these two things. Are the events independent or are the events dependent? Here's your definition. So if you want to pause it for a moment and write these down, these are two really important concepts in probability. The first one says, right, independent events are two events that are independent when the occurrence, two events are independent when the occurrence of one event does not affect the occurrence of the other event. I'll show you some examples here in just a second of independent events. Dependent events then are when two events are dependent when the occurrence of one event does affect the other one. So again, independent, one does not affect the other. Dependent, one does affect the other event. So here's some examples, and we'll decide if these are independent or dependent events. So the first one says, choose a number tile from 12 tiles. So when they say that, they're talking about, like little tiles with numbers on them. You dump them all in a bag or something and you choose. So you choose a number tile from 12 tiles, and then you spin a spinner. So the question is, does the result from your first event, from choosing a number tile, will that affect what you get when you spin the spinner? And the answer is no, right? Those are two completely separate things. Doesn't matter what number I choose, that will not affect what happens with the spinner. So these two we would say are independent of each other. B says you pick one card from a set of 15 sequential number cards. So you got 1 through 15. You pull a number out. Then without replacing it, so you keep that card out, you're going to pick another card. So what you're asking yourself is the probability of the second event affected by what happens with the first one? And this one will. If you think about that for a second, right? If I pick a number card from a set of 15 sequential number cards, say I pick the number 5 and I take that out and I don't put it back, then when I go to draw the next card, instead of being, out of 15, now it's only going to be out of 14, and that number 5 card is no longer available. So what I get on the probability of what happens with the first event, right? It affects the probability of the second event. It changes the odds or the probability of getting something. So those would be dependent. So again, the question you're asking yourself, does the first one affect the second one? I've got, 3 examples here. Let's actually do the first one together. We'll do the one at the top. It says, you roll a standard number cube. They're just talking about a dice. Then you flip a coin. Are the outcomes independent or dependent? Well, it doesn't matter what I roll on the dice. That's not going to affect whether I get a heads or tails when I flip the coin. So one doesn't affect the one doesn't affect the probability of the other one. So we would say independent on that first one. You guys decide this number 1 and 2 if they're independent or dependent. So pause it, make your decision, and then we'll talk about it. So number 1 says, a card is randomly chosen from a standard deck of cards, then replaced. Another card is chosen at random. So if you think of like you're playing cards, if you pull one card out, you could find the probability of getting a certain number. Now the key thing here is that it says it's then replaced. So if I put the card back in the deck again, and then I draw another card, then it doesn't matter what I got the first time. Right? The first event does not affect the probability of the second event. So these would be independent. Now compare that to that other problem we did with cards. If I were to pull the card out and leave it out, then if you don't know, in a standard deck of cards, there's 52 cards. So if I took one card out and left it out, then when I go to the second event, it's changed now because instead of being out of 52, it's only out of 51. So that one would be dependent. One does affect the other one. Number 2, asking a student's age and then asking what year he or she expects to graduate. So the question again is, do those affect each other? Well, if I get the student's age, say they're 16, well then I'm more than likely they're going to be a sophomore, junior. So one does affect the other one. So again, you would consider those to be dependent events. Okay, so independent, one does not affect the other. Dependent events, the one does affect the probability of the other one. So we kind of already did this, but we're going to talk a little bit about actually finding probability. So let's decide if I roll a dice, like I've got here, and I spin the spinner, are these independent events? And the answer is yes. One does not affect the other one. So let's actually find the probability. Let's say I'm trying to find the probability of getting a, so we want to get the probability of getting, say, an even and blue. Okay, so first of all, like we talked about, these events are independent of each other. So if you think about that for a second, when I try to find the probability of getting the dice here, right? Let's do a tree diagram real quick like we did the other day. So I go like this, right? I've got 6 outcomes. It could be a 1, 2, 3, 4, 5, or a 6. And then underneath here, I could get a 1 with each of those colors. So with a blue, blue, orange, black, or red. And then under each of these, you could do the same thing, right? So if you look at that, if you count the outcomes, we've got 4, 4, 4, 4, 4, 4. You got 6 4s, right? We kind of talked about, I've got 6 possible outcomes with the dice, and I have 4 possible outcomes when I spin that spinner. So altogether, there are 24 possible outcomes. Now we wanted to find the probability of getting an even and a blue. So let's count those. I've got an even, which is 2, and then a blue. Sorry, I got a 2 and a blue. That'd be 1. I could get a 4 and a blue. That'd be 2. And I could get a 6 and a blue, and that would be 3. So 3 out of 24. Now what I want to point out is this. If we just found out, if I roll the dice, how many favorable outcomes are there? So how many evens are there? Well, 2, 4, and 6. There's 3 of them. Okay, and then I look at the spinner. How many favorable outcomes do we have there? Well, I want to get a blue, so there's 1, right? 1 out of 4. So I end up with that gives me my total, which is 3 times 1 is 3, right? There's 3 possibilities times 1 possibility. I get 3. 6 times 4 gives me 24. So what we actually end up doing is, all we really did is took, what are the odds of getting an even? 3 out of 6. What are the odds of getting a blue? 1 out of 4. And if I times those together, that gives me the answer. That is how you find the probability of independent events. All I have to do is take the probability of the first one, the probability of getting an even, and multiply it by the probability of the second one. So if they are independent, and I'm trying to find the probability of both happening, of getting an even and a blue, I just multiply the 2 probabilities together. Okay, now I want to point that, I want to compare that to some events that are dependent. So this one says, Mr. Welnick puts the names of each of the persons in the class into a hat and draws out the names of 2 people. Are the 2 events independent or dependent? So this one probably depends a little bit. I wasn't very specific there. Let's say I'm drawing out the first name and then I'm setting it aside. I'm not replacing it. And then I'm drawing out the second name. So that, in that case, these 2 events would be dependent, because if I take out, when I draw out the first one, instead of having, say there's 20 students, instead of having 20 students, now there would only be 19 for the second one. So the first event affects the probability of the second one. So these would be dependent. So if I want to find these, here's how I do it. I start out by saying, what would be the probability? Oh, let's say, what are the probability of drawing out, let's say, a girl first and then another girl. So a girl first and a girl second. So I guess I need some more information up here. Let's say that there are 20 students and 10 are girls and 10 are boys. Okay. So when I draw out the first person, the probability of getting a girl, that would be 10 out of 20, right, or a half. Okay, and then we're going to multiply that. Now this is, if they're dependent events, this is how it changes. Instead of multiplying it by the probability of the second thing, of getting a girl right there, what I do is I multiply it by the probability, of getting the second thing, given that the first thing already happened. So we're assuming, you have to assume, that I already drew out a girl's name. That's already happened, and I set it off to the side and I didn't replace it. So now when I go to draw out the second girl right here, there's only going to be 9 girls left in there, and instead of being out of 20, it would only be out of 19. Okay? And we'll talk a little bit more about this, but again, if they're dependent, you take the probability of the first one and you times it by the probability of the second one, given that or assuming that the first thing already happened. And we could times those together. What's that, like 90, 90 out of, what's that, 380? And we reduce that, be 9 out of 38. That'd be my answer as a fraction. We could change that to a decimal or, or a percent if we really wanted to. Okay, so what we're going to practice with over the next little bit is how do you find the probability if the events are independent? That's the simplest one. And how do you find the probability if the events are dependent? Here's a little formula you can write down. So if the events are independent, right, I want to find the probability of A and B happening, and they're independent, right? They have to be independent of each other. Really simple. I just take the probability of A times the probability of B. I have my answer. If the events are dependent, it's a little bit different. And to understand that, I need you to write down this definition first. We haven't talked about this, but put down conditional probability. Conditional probability is the probability that B occurs given that the event of A already occurred. So the way we do that is, I'll write this with symbols. You say the probability of B happening, and if you draw this straight line, that means given that A has already happened. So on that last problem is, we could say, what's the probability of drawing out a girl's name given that we already drew out a girl's name? Okay, so what's the probability of B happening given that A already happened? So make sure you have that definition. If you need to pause it, you can, but have that definition of conditional probability written down, and make sure you've written down that notation also. So here's our formula. If 2 events, now we're talking about dependent events, happen, we still multiply them together, right? If I want to find the probability of A and B, I still take the probability of A times by, the only difference is I times it by the probability of B given that A already happened. So when I find the probability of the second event, I have to assume that the first event already happened, and I have to adjust that probability accordingly. So here's the example, using that example I just gave you, right? The probability of a girl first and a girl second. I first just find the probability of getting a girl first. And these numbers are going to be different because this is a different problem the book used. That was what, 10 out of 20 on our problem? Then I times it by the probability of getting a girl second, given that I already got a girl. So if I already took out a girl's name, I only have 9 girl names left, and I only have 19 total names. Okay, so I times those together and get my answer. So they're really similar. When you see the probability and you're thinking of and, you want both things to happen, you're thinking multiplication. If they're independent, you just multiply the probabilities together. If they're dependent, you multiply the probabilities, but you have to adjust that second probability, assuming that the first one right here, right? Assuming that first one already happened. I'm going to skip over this problem, and we're going to go to this one right here. It says, as part of a board game, you need to spin the spinner, which is divided into equal parts. See those 8 equal parts. And then find the probability that you get a 5 on your first spin and a number then greater on your second spin. So whenever you see that and, you're trying to find the probability of both happening, you should be thinking multiplication with probability. The second thing you have to decide is, are they independent or dependent? Well, it doesn't matter what I get on the first spin. I could get a 1, 2, 3, 4, all the way to 8. It doesn't matter. That will not affect what I get on my second spin. So these are independent. Okay. So since I know they're independent, all I do is find, right? I want to find the probability that I got get a 5 on the first spin and a number greater than 3. So we want a number that is greater than 3 on the second one. So because they're independent, I just find each one separately. Probability of getting a 5, well, there's only one 5. so it's 1 in 8, times by, times because of the and, getting a probability of getting a number greater than 3. So a number greater than 3 would be a 4, 5, 6, 7, or an 8. So there's 5 of them, so it'd be 5 over 8. Okay, if we multiply those together, we end up with 5 out of 64. Again, you could change that to a decimal if you wanted. What's 5 out of 64? It's going to be 0.08 if I round it off, approximately, or an 8% chance. Okay, this one says a bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill out of the bag, set it aside. This is important. You're setting it aside. And then randomly draw out another bill from the bag. Find the probability that both events A and B occur. So event A is you draw out a $100 bill. Event B is you draw out first. The event B is the second time you also draw out a $100 bill. So if you write this off to the side, I want to find the probability of A and B happening. So the and tells us multiplication. Now, the thing you have to be careful with here are these events independent or are the events dependent? Does the probability of the first one affect the second one? Well, because we're setting it aside, if I take out a $100 bill, that will change the probability of getting another $100 bill. So these are dependent. So my formula is this. I take the probability of A happening, of getting a $100 bill, and I times that by the probability of B happening, given that A already happened. So what's the probability of A happening? How many $100 bills were there? There were 5. How many dollar bills are there altogether? Well, it says there's 20 ones, 500, so there's 25 altogether. Okay, we're going to multiply that. What is the probability of B happening given that A already happened? So we're assuming that I already took out a $100 bill. So if I already took out a $100 bill, now there's only 4 $100 bills left. And now instead of being 25 total, there's only 24. So if you multiply those together, that should give me my answer. So what's that? 1/5 if I reduce that. This one is 1/6. So you have a 1 in 30 chance of drawing out a $100 bill twice in a row, okay, if you don't replace it. Okay? So again, it comes down to if it's dependent, you have to adjust that second number, okay, when you go through and find it. Okay, let's look at this one. It says you randomly select 3 cards from a standard deck of 52 playing cards. What is the probability that 3 cards are hearts? That all 3 cards are hearts when you replace each card before selecting it and you don't replace the cards before selecting it. So these are 2 different problems. So look at part A. If you replace the cards, that means I draw a card out and then I put it back before I draw the second one. If I do that, that means that they're independent because it doesn't matter what card I draw out the first time. If I put it back before I draw out the second one, then it doesn't affect it at all. So A is an independent event. So let's do A. So if I draw out, I don't know how well you know hearts cards, but they're divided into 4 suits. You know, so if you go 52 divided by 4, there are 13 heart cards. So I go to draw my first card, I have a 13 in 52 chance of getting a heart. When I put that one back and draw again, I'm going to have a 13 in 52 chance again. And my third event, if I put that card back and I draw again, for my third one, I'm also going to have a 13 in 52 chance. By the way, 13 over 52 reduces down to be 1/4. So really it's 1/4 times 1/4. So the probability of getting all 3 hearts is 1 in 64. Okay, that was for part A. All right, now for part B, we're not putting it back. We're not replacing it. So if I draw out the first card, when I go to draw the second one, it changes my odds because now there's no longer 52 cards and there's not 13 heart cards. So what we're going to do is go like this. When I draw out the first card, it's the same. You have a 13 in 52 chance. But when I go to draw out my second card, I only have a 12 in, because I took out a heart, right? You assume that the first event happens. We're assuming we got a heart card. So there's only 12 left, and there's only 51 total. And I drew out another heart, so now I'm assuming that there are only 11 hearts left, and there's 50 total. Okay, let's do that. I'm just going to use a calculator for that. So I'm going to go 50 seconds times by 12 or 51 times by, hold on just a second here, times by 11/50ths. And when we do that, whoops, sorry, just screwed up. We do that, we end up with 11/850. My calculator's kind of hard to see here. I'm just going to do a decimal. It ends up being approximately 0.01. Our previous answer, 1 out of 64, ends up being, oh, they're close. This one is 0.02 if you round it off. Okay. So if you're replacing a card, you're slightly more likely to get 3 hearts if you replace it than if you don't replace them as you go. So again, I just want you to compare those two, like what happens if the events are independent or dependent. If they're independent, you just do each one separately, times them together, each event. If they're dependent, then you've got to adjust these events as you go. Assume that the previous one happened and you have to adjust it. We're not going to do all of these, but let's do number 4. It says an example 4, that was the money example. We had what? We had 20 $1 bills, and we had 5 $100 bills. It says, what's the probability that both bills are $1 bills? And if you remember, and now I can't remember if we were replacing those or not. Let's look back at the problem and see what it said. Oh, you're setting it aside, so we're not putting it back. So when I go to draw out my first dollar bill, I have a 20 and 25 chance of getting a dollar bill. And I'm not putting it back, so I'm setting that aside. So now remember, for my second, these are dependent. For my second one then, I no longer have $20 bills, now I only have 19. So it's 19 out of 24. Again, I grab my calculator, I times those together. So 20, that's 0.8 times by 19 out of 24. It comes out to be, as a decimal, my probability is about 0.63 is what that answer comes out to be. Okay, so kind of think about that. First decide, independent, dependent, right? If it's an AND problem, which all of these are, you've got to find the probability of the first one times by, if they're independent, times by the probability of the second one. If they're dependent, you find the probability of the first given that the second really did happen. Okay, the last part we're going to do here, well, actually, let's do this problem first, and then we'll move on to conditional, which is the last part. It says a group of 4 students included 1 boy and 3 girls. The teacher randomly selects one of the students to be a speaker and a different student to be the recorder. Use a sample space to determine whether the randomly selected a girl first and randomly selecting a girl second are independent of each other. So this is kind of working backwards. If they're independent, then remember the probability of A times the probability of B has to equal the probability of A and B. So we can kind of use this to test to see if they're independent or not. So let's find the probability first of just the first event happening. So we want to randomly select a girl first. So to do that, look up there. It says a group of 4 students includes 1 boy and 3 girls. And you randomly select one to be a speaker. Okay, so the speaker would be, there are, what, you want to select a girl first. So there'd be 3 girls out of 4 total. Okay, and you want to times that by, what's the probability of the second event? So if you look at that, it says the second event was selecting a girl second. So That would be, and we're going to find that just separate. That would also be 3 out of 4. So that ends up being what, 9 out of 16. And the question is, does that come out to be the same thing as I get in my sample space over here? And they've written it all out for us, right? You get a girl first, boy, girl second, boy. There's only one boy, right? So they listed all of these out there. And we want to find what is the probability of getting like 2 girls, right? So here's all the ways you get 2 girls. So you've got 2 right there, 2 right there, and 2 right there. So you've got, this is the number of times you end up with that. Oh, this is the number of girls. So these are the number of ways you can do it. There's 1, 2, 3, 4, 5, 6. So that would be 6 out of, and how many total outcomes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the question is, are those equal to each other? They're not, right? 9/16 does not equal 6/12. That means this didn't work. The probability of A times the probability of B did not equal the probability of A and B. So the question was, are they independent? And the answer is no, because they were not equal to each other. So that's kind of a way you can kind of test to see if 2 things are independent or dependent of each other. Let me show you another example. I'm going to go back here just a little bit. One I skipped over, but this is a good way to show this. This says if the probability of event A is 0.2 and the probability of event B is 0.5 and the probability of A and B is 0.1, are they independent? So again, we just use that formula. If I take the probability of A times the probability of B, if they're independent, then they'll equal the probability of A and B. That's what we're testing. So what was the probability of A? 0.2, 0.2, times by the probability of B, 0.5, 0.5. And the question is, does that equal the probability of A and B, which is 0.01? So I don't know, grab a calculator and times those together. 0.2 times 0.5 equals 0.1. Yes, it does equal it. Checks off. That means, yes, they are independent. So you can kind of see, if you know they're independent, you can use a formula, but you can also use a formula to prove that they are independent or dependent. Okay, we have one last thing to cover. I know this is kind of a longer lesson. I apologize. But we do need to talk just at the end here a little bit more about conditional probability. So we're going to find conditional probability. Remember, we wrote this down already, but conditional probability is the probability that the event B occurs given that A has already occurred. And that our notation for that, remember, the probability that B happens given that A already happened. So let's look at this one right here. It says a quality control inspector checks for defective parts. The table shows the results of the inspector's work. And it says find A, the probability that the defective part passes. So let's do that one first. So notice this one, it says the probability that a defective part passes. It's already telling us then that it's a defective part. So when I come and look at this chart, I'm not looking at all of them. Like, I'm not looking at all 4. I already know that it's a defective part. I'm only looking at these right here. So out of those, I want to find what is the probability that it passes. Well, if you look on there, 3 of them passed. Out of a total, how many defective parts were there altogether? Well, there were 3 that passed and 36 that failed. So there were a total of 39. So the answer for part A, what is the probability that a defective part passes? Well, that'd be a 3 out of 39, which is 1 out of 13, which you could find a decimal on that also. Okay, so let's look at B. It says, find the probability that a non-defective part fails. So we already know that it's non-defective. That means we're not looking at all of them. We're only looking at those guys right there, the non-defective one. And we want to find the probability that it fails. Well, how many of those failed? 11. Out of, what was the total? Well, how many total parts were non-defective? If we add those together, 461. Okay, so that would be our answer. Again, we could grab a calculator and plug that in there and find a decimal. So conditional probability, you're assuming something already happened. So in this case, On that last one, we knew it was given to us that it was non-defective. So we narrowed down, instead of looking at all of them, we just looked at the non-defective ones. Okay, so that's the condition. It's something that was already given to us. There's also a formula. I'm going to show this to you. We're not going to use this a ton, but write it down. We already know this, right? If two events are independent, if I want to find the probability of A and B happening, okay, I take the probability of A times by the probability of B given A. Let's say, though, that I want to find some condition. Let's say I want to solve for this. If I want to find the probability of B given A, what I can do is I can take this formula and I can divide by the probability of A to cancel that out. But that means I have to divide it over here. So this is the formula for conditional probability. So pause it for a second when I get done here and write this down. If I want to find the probability that B happened given that A already did, I take the probability of A and B and I divide it by the probability of the given, the probability of A. So again, have that formula written down. You'll have a problem or two on your assignment where you're going to have to use that. Okay, let's try this one right here. So it says at school, 60% of students buy a school lunch. Only 10% of the students buy lunch and dessert. What's the probability that a student who buys a lunch also buys a dessert? Okay, so this is important. It says a student who buys a lunch. That's given to us then. We're saying we're only looking at those that buy a lunch. What's the probability that they also buy a dessert? So it would look like this. What is the probability that they buy a dessert given that they already bought a lunch? So what's the probability that they buy a dessert? And we already know that they bought a lunch. We're only looking at the people that bought a lunch. So here's our formula. We go like this. What's the probability of getting dessert and buying lunch divided by the probability of or divided by the probability of buying a lunch. So this is my formula. If you read through the problem, it gives us the answer. It says, at school, 60% of the students buy a lunch. That's this right here. Probability, so that's going to be on the bottom. I'm going to write it as a decimal. 60% is 0.6. Right, that's the probability of someone buying a lunch. Only 10% buy a lunch and dessert. Hey, that's this up here. You bought a lunch and a dessert, both. So that was 10%, so that'd be 0.1. So we grab a calculator, we plug that in there, we go 0.1 or divided by 0.6, and we get approximately, I'm going to round that off, 0.17. Okay, that's the probability that they're going to buy dessert given that they already bought a lunch. In other words, what you're saying is instead of looking at all the students, you're only taking it out of those that bought a lunch. These are tricky, so let's do one more of those. I'm going to do number 7. Number 6 isn't bad, you're just using that table. But 7 says at a coffee shop, 80% of customers order coffee. Only 50% of the customers order coffee and a bagel. What's the probability that a customer who orders coffee also orders a bagel? So what they're saying is you're looking at just the people that ordered coffee. That's the given right there. Right? You're only looking at those that ordered coffee. What's the probability they ordered a bagel? So I'm going to write that down. The probability that they ordered a bagel, given that they ordered a coffee. Okay, set up our formula. The formula is this. The probability of a bagel and coffee divided by the probability of the given. The probability that they ordered coffee. And it will tell you these numbers in here, right? At a coffee shop, 80% of the customers order coffee. Hey, that's that right there. So that's going to be 0.8 on the bottom. Okay, what's the probability of ordering a bagel and coffee? About 15% ordered a bagel and coffee. So I got 0.15 divided by 0.8. Again, plug that in your calculator, and you end up with about 19. 0.19 is about what it comes out to be. So those are a little bit tricky, but use the formula, write it down there. So here's your main ideas. If the events are independent, you just times the probabilities together. If the events are dependent, you still times them together, but you have to adjust each probability as you go. So you assume that the first thing already happened. What's the probability of the second thing? okay, before you multiply it. With conditional probability, just remember what you're doing is you're narrowing down what you're looking for, right? Instead of looking at all the customers, you're only looking at those that bought coffee. And we're just, if you write it this way, right, the probability of getting a bagel given that they ordered coffee, then you can just use our little formula and plug the numbers in there and get that. Let me know if you have questions. Thanks. Good luck.